Welcome back to video lecture series on sensors and actuators. This is the module 5. So in this module 5, we are going to see what is microsensor and microactuators. So in the previous modules, module 1 to 4, we have seen all the sensors classifications and in the classifications of different types, what are the methods and applications and operations for various types of sensors. And in actuators, what are the different types of actuators? Everything I've seen in the last 4 modules. So in this module, whatever we have seen, those sensors, how the micro sensors and micro actuators are formed, what are the classifications in using these micro sensors and micro actuators. So I'm Dr. Yasunta, Assistant Professor in the Department of Electronics and Instrumentation Engineering, SRM Institute of Science and Technology. Let's move on to the next slide. So these are the topics I'm going to cover in this video. The microsensor. So what is the basic principles of microsensor? What are the examples? The same way we can go for this microactuators. And what are the different types of microactuators? And so how these actuators are formed? What are the various fabrication techniques involved in making these microsensors and microactuators? So this covers this, and these are the topics we'll cover in this module 5. So before I move into the microsensor, first you should know what is MEMS. So MEMS is nothing but micro-electro-mechanical system. So any engineering system always it performs some electrical mechanical functions. If those components of electrical mechanical functions, if it is in micrometers, then we call that as MEMS, micro electromechanical. That is both the combinations of electrical and mechanical, forming that if it performs the electrical and mechanical functions in micrometers, then we call that as MEMS. So 1 micrometer is nothing but 1/10th of the human hair. That means that much of very smaller in size. So these are all some of the available MEMS products in the market. In microsensors, we can have acoustic wave, biomedical, then chemical inertial sensors, and optical pressure sensors, then radiation and thermal. These are all some of the microsensors available in the market. And coming to the microactuators, micro valves are there, pumps and microfluids, both electrical and optical relays and switches. These are all in micro. That means it's a rice size, the size of the rice grain. So that is the actual size of the sensors. So now let us define what is a micro sensor. So it is nothing but my miniature device, it's a very small device. So the same principle what happens in sensors. So it will detect the physical, chemical and biological properties and convert into an measurable signal, electrical signals. So the same thing has happened here, but it should be in miniature size. So that we call it as micro sensors. The same case for the actuators. Actuators, it has to create some motion. How it creates a motion in miniature size. That's all. Both are same. Only thing is we are converting all the sensors into a miniature size. For that, various fabrication techniques are involved. All these things we are going to see in the further slides. So how small are the MEMS device? What is the size actually? So it is the size of the rice grain, or even it is very smaller. So some examples I can say that inertial sensors, that is, so in airbags we have the inertial sensors. So that is of very it is of rice grain size only. That's will be placed in the inside the airbag. And microcores, these are some of the examples of MEMS devices where we have the combinations of both electrical and mechanical components in miniature size. So now we'll see how the airbag works with the this micro sensor. So this is the micro sensors. It is of the 3 mm into 2 mm. That is the actual size. That means see how much small the sensor is. So this is what's kept in the inside the steering wheel. This is the micro inertial sensor in place. This will be placed in the micro inertial sensor is placed here. Okay, so this is the size of the this is the sensor chip. This is the sensor chip. It is of very smaller size. So whenever the crash happens, what will happen in the car? Inside you have a crash sensor. The crash sensor, it gets sensed and it gives the signal to the airbag activation unit. So inside the airbag activation unit, we have one inflator. The inflator is nothing but it is a chemical uh, propellant. So this chemical propellant, what it has is, so this will fills the nitrogen gas which is present inside the airbag. So once when it hits this sensor gives the signal to the inflator immediately it will fill the nitrogen gas within 20 to 30 milliseconds. It's such a very fast it will fill, and this will makes the it will once it fills immediately it will get open. So that's why we are protected from the many of the accidents. Instead of falling our head into the steering wheel, suddenly it will falls into the airbags. So this is what the nowadays we have the initial sensor that is placed inside the airbag deployment system, where it is of very miniature size. There is a sometimes you may wonder how this airbags opens. So immediately when it crashes, the inflator will fill the gas, and suddenly the airbag will open, and that will protect. Everything happens within the milliseconds. That's the reason many accidents are even if you wear the seat belt will once you wear the seat belt, then the airbags will work. So it will prevent many people lives. This is a Denso Research Laboratory. They have in Japan. They have made the micro cars. This is of only this much size, only the rice grain size. This is one of the micro car. So what are the enabling technologies for miniaturization? So I can say this microsystem technology, it has the range of the size from 1 micrometer to 1 millimeter. And this miniature device is always, it's between 1 nanometer to 1 millimeter. But initially we had this 1 micro to 1. Now it's moved on to 1 nano to 1 millimeter. So when I say nanotechnology is being an emerging technology now. The size is from zero point 0.2 nanometer to zero point 0.1 micrometer. See the size. It's very, when I see this 1 nanometer, is nothing but the span of 10 times hydrogen atoms. 10 into hydrogen atoms, that much of small size. So these are all some of the that is miniaturization of this size that is used in the miniature devices. Next, MEMS as a microsensor. How can we say MEMS, micro-electromechanical system, as a microsensor? So sensor is nothing but it just sends the signal, and when I give an input, it just sends the signal, and the same whatever the sense it will be sensed in the microsensors, sends the signal, and once it gets sensed, it should be converted to electrical signal by using some transaction will takes place. Transaction means converting the signal into some usable standard range of signals. So you have a transaction unit, that conversion will be given as an output. So this we call it as a microsensor. The same as in the sensor, there you have the input signal, it just sensing element will be there. Then transaction converts that signal output into some usable or standard electrical signals. That is what the output you will get. So these are all some of the examples of the micro pressure sensors. It is of coin size, our 1 rupee coin. That much of size is this micro pressure. Nowadays we have various pressure sensors that is not of that much size. It's only when compared to micro sensors, those sensors have some size, some bigger size only. Now we can convert those things into a miniature size, so that will help us to it will add, this will avoid the more number of spaces will be avoided by using this type of micro sensors. So MEMS is a microactuator. So we have the microactuator. Once the sensor output come, the sensor output will goes to the controller. Controller give the signal to the actuator. What signal it will give? Whatever the error happened in this controller, it will take the decision, and then it gives some action uh, to the it gives the signal to the actuator. What the actuator does, it will do, it will create some motion to perform the signal that what it received from the controller. So that is what is this. This output action is nothing but the controller output. That will be goes to the micro, that is the actuating element. So once the controller, whatever the controller gives the signal to the actuator, actuator performs and gives the motion, and finally, final output will again it convert into an standard electrical signal. So this is what is the micro actuators. So the Lego process, they have developed the micro motor. There's the micromotor. Everything will be in a very small size with stators, rotors, and you have the gear options. All will be connected, and it makes us many miniature size motors. So next comes the components of micro systems. So as I said before, micro system, you have two things. One is the sensor and the actuator. A sensor, what it happens, it will sense the signal, gives the signal, and then it undergoes transduction. After it undergoes transduction, then it goes to the processing unit. It's a controller. From the controller, it goes to the actuator. Okay, so this is the actual process. So this we call it as micro system. From the sensor, it goes, sensors and sends the signal and gives the signal to the, convert the signal into standard signals, and then it goes to the processing unit, that is the controller unit. From the controller, output will gives the decision to the actuator. So the actuator creates a motion and it performs its functions. So next comes the so before you're making all these what is that micro sensors and micro actuators, we have to follow the fabrication techniques what are all used in this micro in these actuators. First, let us see with the what are the techniques that is we are adopting in this fabrication. The first step is substrate selection. So before we are forming any thing, any sensor thing, first we have to form a substrate. Substrate is nothing but we have to form whether it is a silicon substrate or a nickel, silicon, aluminum. So based on the what type of insulator we are using, that substrate we need to form. So mostly we will use only the silicon substrate. Other things we can use the glass, polymers, and silicon or insulator we can use. So this is act as a base, the first layer base where we want to build the remaining structures. So that is the substrate selection. And second one is the thin film deposit. Once the substrate is formed, next we have to form one thin film deposition we have to make. So it is used to deposit. What is the reason is to deposit it, you have to conduction should take place, and the insulating as well as the piezoelectric layers. Anything, any type of deposition we can make in this. So these are the techniques we can use for this thin film deposition. One is the PVD, physical vapor deposition, and the next one is CVD, chemical vapor deposition, or else we can use this spin coating as well. So these are the different methods are used for the deposition of the layer. So the deposition of the layer, already you have a silicon, and so over that silicon substrate you have to make a SiO2 layer, silicon dioxide layer we have to form. So what is the use of these making the SiO2 layer on the top is, so it is act as an insulation layer. So it will prevent any further for foreign bodies or any other bodies, any other elements will, it should not affect the substrate. For that we have to use one, this is a preventing layer for the substrate. So always we have to use SiO2 deposition layer. And the next technique is photolithography. So it's nothing but it is a process of forming a pattern. So already we have one surface. In that surface, we have to form a pattern. So what type of pattern you want? Based on the sensor shape, another thing, we have to form a pattern by using light rays and photoresist. So this technology is called as photolithography. So there we can have following steps. Here you can see the steps involved in this photolith. The first one is film deposition. So already I said film deposition, first you have to form a silicon layer, silicon substrate. Upon the silicon substrate, you have to deposit one thin layer for preventing any foreign bodies to not destroy this. So we are having a SiO2 layer that will be deposited on the top. And then you have to use a photoresist coating. This is the photoresist coating. So that means a light sensitive polymer is spin coated on the wafer. This is the wafer, right? SiO2 wafer. So on the top of the SiO2 wafer, you have to form one photoresist coating, okay, on the wafer. And then after forming this photoresist coating, next one is mask alignment. So when we have to use a mask, suppose if we want to make we have the entire thing is coated. So in that only particular region only we want. So we have to use some mask, so we have to prevent those areas should be used in further for the further process, and the remaining areas is not the unwanted things we have to remove. So for that you have to use some mask. So here the mask is used. So one, two, these three regions you want. The remaining regions is not needed. So that using a mask, and these are all the transparent layers. And then now you apply the photolithography. That means you have to sunlight or UV rays pass onto this mask to alter. Already you have the photoresist to alter the photoresist. So this entire layer will be masked, and these in these trans the light rays will fall on this mask. So nothing will happen in this mask, but this will penetrate into this and will move towards this photoresist. So now after applying these UV rays, you will get the development like this. So this is called as edge mask. Okay, so these are the shapes we want. But now what is the next step is, I want only these areas to be removed. These areas to be removed. So what I will do, the first in the photolithography, I have removed, instead of this entire surface, I have removed these regions. Now I want to remove the remaining regions by applying etching process. So that is what is the etching process. Okay, so etching is nothing but a removal of the unwanted materials in the to shape the micro structure. So now this is the development procedure. From the developed procedure, I want to remove these regions by using this etching process. So how this etching process is used is, they're using the wet material. This material should be removed by using some chemicals. By they will immerse those things into a chemical solution, that is potassium hydroxide. If we use a potassium hydroxide, these will penetrate into this and remove all these regions. So now you will get the region like this. So if it is a wet material, means it is removed by using a chemical solution. If it is a right material, you have to dissolve using some vapor process. So these are the different materials based on what type of material it is, whether it is wet or dry. Based on that, we have to use for the etching process. Once this is done, that's all. So these are the fabrication process. Finally, we'll have, using this micro machining technology, we can we can make the micro sensors with a range of 1 to 500 micrometers. 1 to 500 micrometers. So they will help to achieve the desired dimensions of the final microstructure. So these are the whatever we have seen. The first step is for have a substrate. After the substrate, you have to make a insulation layer, for the prevention layer, SiO2 layer, and then you have to make a photoresist, and then use a mask, then apply the photolithography UV rays to remove those regions, and then use some etching process to remove the remaining unwanted regions. Then you will get one shape. So this is the actual fabrication process of any micro sensors. So next comes the micro actuators. So it is again the same thing. It is a miniature device which converts the any type of energy like electrical, mechanical, electrical, thermal, or magnetic into a mechanical motion. So the mechanical motion is typically a displacement of force or torque. So all these output will be in a nanoscale, nano or micro scale. So these are the different types of micro actuators. One is the electrostatic micro actuators, then piezoelectric micro actuators, then thermal micro actuators, and magnetic micro actuators. We'll see one by one. So the first one is the electrostatic micro actuators. So it is electrostatic force is first you should know what is electrostatic force. Electrostatic force is nothing but it is a force of attraction or force of repulsion between any two objects. So whenever if you're placing any two objects, these objects has an electromagnetic field, automatically what will happen? There will be a attraction will take place or maybe a reflection. So that force is called as electrostatic force. So in MEMS and micro actuators, usually these attractive forces usually it will be generated between the two conductive or opposite charged conductive surfaces. That surfaces it may be capacitor plates where we want to, when voltage is applied to this, what will happen? These plates based on the thing, it will the distance may vary. When the distance changes, automatically there is a change in the capacitance. So this is what is the electrostatic micro actuators. So here you have the two this one is the two charge objects. This is one object, this is another object. When you apply voltage, what will happen? The plates which has the it will move towards the magnetic field, and due to that these electrodes are pulled and insulated from each other through the electrostatic, because this is insulated, both are insulated. So when a driving unit, when voltage is applied, what happened? A wave like electrodes, this is the wave like electrodes, okay, that is pulled because of this electrostatic force. So where we can apply this is we can apply this in micro mirrors and switch circuits in MEMS RF switches, and in tuning the capacitors we can use this electrostatic micro actuators. So next one is the piezoelectric micro actuators. This is device that converts electrical energy into mechanical motion using piezoelectric effect. So piezoelectric effect, you have a piezoelectric element. So when you apply voltage is applied, what happens? It will undergo a deformation. Due to the deformation, that how much amount it gets deformed, that will be converted into an electric field. So that is the actual principle of the piezoelectric element. So common material we use is the lead zirconate titanate, that is PZT, or else we can use this quartz. And these are the electrodes. These is the one electrode, this is the second electrode. Mostly they'll use either a silver or gold, and then silver or the gold, and then voltage is applied on the top as well as the bottom. So this piezoelectric element undergoes deformation. That amount of deformation gives the change. So this is the actual micrometer micro actuators, piezoelectric micro actuators. So it is a 1 centimeter size. It is designed. It is designed for the purpose of using those micro actuators in the pressure sensors, or wherever for analyzing the pressure sensors, we may have the piezoelectric sensors. Okay. And applications are the precision processing systems, micro speakers and buzzers. They can use this, and medical devices. We can have the application for micro actuators, piezoresistor. Next one is the piezoresistor micro actuators. It is a device that converts electrical into mechanical motion, but using piezoresistor material. That is piezoelectric material, but this is piezoresistor. So piezoresistor means it produces some changes in the resistance. Whenever any mechanical strain happens, it will produce a change in the resistance. So piezoresistivity, it has the property to change their electrical resistance when there is any mechanical stress is applied. So commonly used MEMS for sensing strain. For sensing strain, we use only this piezo resistivity. So piezoresistive microactuators is integrate strain sensing with microactuations, and the piezoresistive, the same type we have. We have piezoelectric, the same type of sensors we have for the resistivity, and here this is the structure of the piezoresistor. So it is as it is this is doped with silicon or polysilicon to change there. Whenever the voltage is applied, it undergoes deformation and it changes its resistance. That is the characteristics of this piezoresistivity. So here This will be used in cantilever and bridge. So whenever voltage is applied to this actuator structure, it undergoes deformation, that is due to thermal, electrothermal or else electrostatic forces. So due to that, it detects the how much amount of strain happens by changing the resistance. So when this is applied, it undergoes deformation, how much amount of strain we are applying, that much amount of change in resistance will take place. So next comes the thermal micro actuators. So thermal micro actuators device that moves when heated. Whenever heat is applied, it moves. So based on that, we have to define this thermal micro actuators. This is caused by thermal expansion. Okay, so using the fabrication techniques, we have to make this thermal micro actuators. So they have here you have this bimetallic strip. One is material A, another one is material B. So when heat is applied, what happened? This material, based on the coefficient, the material will expand. So how much amount of deflection takes place? The deflection will be equivalent to the change in the temperature. So here the application we can see in optical systems, we can have this, and biomedical devices and inkjet printers, we have this thermal micro actuators. Next is the magnetic transduction in micro actuators. So magnetic transduction is nothing but how much based on the magnetic fields, it will generate a mechanical motion. So that is called as magnetic transduction. These actuators are also a part of MEMS, and it's always operate with the help of Lorentz force. So Lorentz force is nothing but we have a current carrying conductor. This is a magnetic field is placed perpendicular. It produces some force. That force is called as the Lorentz force, which is equal to I into B. Y is the current vector and B is the magnetic field. So this will be used in the Hall effect transducer. The working is same as we have seen previously. Then electro position sensing circuit. The electro position sensing circuit is nothing but it will detect the actual location or the movement of an object. So it will just detect and then convert into an electrical signal. So that is called as electro position sensing circuit. So there are different types of sensing circuit. One is the linear, rotary, and proximity. So linear already you know it is a straight line motion, and rotary it is an angular motion, and proximity is nothing but the presence of detection. So whether the person is present or the metal is present or any non-metallic objects, so it will detect those things. So that is called as electro positioning sensing circuit. The types of position sensors are already we have seen all these things in the previous modules. The potentiometer, then Hall effect sensors, then LVDT we have seen, and capacitive and inductive sensors. So all these position sensors. So we know that potentiometer means it's based on the slider moves or by adjusting the potentiometer, it will produces changes in the resistance. So that is potentiometer. And Hall effect sensor, what it happens, it will detect the based on the magnetic field, it will determine the position. And when it comes to the LVDT, linear variable differential transformer, so based on the displacement, it will measure the displacement. That's based on the how much amount of magnetic induction takes place between the two coils. Based on that, it undergoes displacement. So that is linear variable differential transformer. And capacitive or inductive is, so based on the distance changes, it will alter the capacitance as well as the inductance. So that is what you have seen in the capacitive or the inductive sensors. So these are all some of the examples which is given. Already you have seen all these things in detail in the previous modules. Just go back those modules and go through the how the potentiometer works and how this LVDT works in the case of position sensors and Hall effect sensor and capacitor sensors in positioning and then inductive sensors. These are all some of the technologies where we can use all these sensors can be used in the position sensing. So thank you for watching my modules, module 1 to 5, module 1, 2, 3, 4, and 5 of sensors and actuators. Have explained all the sensors, its characteristics, then classifications, then micro actuators, what is its methods, and always the and as well the sensors, microsensors and micro actuators, and how the fabrication takes place in all the sensors, microsensors. I hope you all enjoyed my the videos, and thank you for watching. I thank you for watching my video, and I hope that you all have understood the concepts explained in all these modules. Thank you once again.